Example 1.4.4. A magnet is moving such that it creates a time-variant magnetic field with dB/dt equals 0.4 Tesla per second. The magnet moves through a 5-turn coil with a cross-sectional area of 0.002 square meters. Determine the induced EMF in the coil. So this is our example to kind of dig into and better understand Faraday's law of induction. Any generator, the generation action is based on a moving magnetic field or a coil that moves in proximity to a magnetic field. And so this is the basic kind of science by which all electricity is generated, this concept of Faraday's law of induction. It's all based on this concept of magnetic field strength. That comes from dB/dt. So you'll recall from the reading that B stands for magnetic flux density. That's kind of the strength of a magnet, B, and it's usually measured in units of Tesla or Webers per square meter. And voltages are generated when there is a changing magnetic field strength or magnetic flux density. So that's where that dB/dt comes from. That's the rate of change relative to the coil of the magnetic flux density B. So we're going to start digging into this problem, writing our givens. The first is that the rate of change of the magnetic flux density dB/dt is 0.4 Tesla per second. And I just wanted to remind you that a Tesla is 1 Tesla is equal to 1 Weber per square meter. So this is the unit of magnetic flux density. Again, it's just how strong a magnet is. A stronger magnet will have a larger beta. Think of those as the number of magnetic field lines that are being produced by that magnet linking from the North Pole to the South Pole. Stronger magnets will have more of them, and they'll have higher magnetic flux densities. And then I just want to remind you that the 1 Tesla is just a modern unit for a Weber per square meter. If you have an old textbook from physics, Teslas won't exist. Magnetic flux density will be measured in Webers per square meter. N is just the number of turns in the coil. It's a multiplicative factor. And then A is the cross-sectional area. What is the area that is perpendicular to the magnetic field lines? So the equation we're going to use is Faraday's law of induction, which tells us that the voltage induced in a circuit via a time-variant magnetic field, we call that an EMF. So it's just a generated voltage that will appear in a coil of wire if it's exposed to a time-changing magnetic field. So we want to find what that EMF is. And Faraday's law of induction tells us that we can find the EMF by taking the negative of the product on the number of turns in the coil. So how many loops of wire are there? And we multiply that by what's called dφ/dt, which is the time rate of change of the magnetic field, or the magnetic flux, people would say. And so we weren't given that in the problem statement, and that's because we can calculate magnetic flux, total linked flux in a coil of wire, and that's just A times B, where A again is the cross-sectional area perpendicular to the field lines, and B is the magnetic flux density. So in the text I actually wrote A cosine of theta B, just to remind you that it's the perpendicular flux, which is what's important for A. So in the problem for Faraday's law of induction, we need dφ/dt, not phi itself. We need to know what the rate of change of magnetic flux is. We can get that one of two ways. Either we have a changing cross-sectional area with a constant magnetic field strength. So this would be the case in a coil of wire that was spinning in between two magnets. Or we can get this from a dφ/dt from a constant cross-sectional area but a flux density that changes. Somehow we're able to change the field strength, the magnetic flux density, and that's what we're dealing with here. Is we're going to deal with that second equation. The rate of change of magnetic flux with respect to time is equal to the cross-sectional area times the rate of change of magnetic flux density with respect to time. So we can just plug that into Faraday's law of equation. The generated EMF is negative N times A times dB dt. So now this problem becomes a simple matter of plug and chug. We get minus 5 times 0.02 square meters, and we need to multiply that by 0.4 Teslas per second. So we immediately notice we have a unit cancellation problem here, and so that's why I introduced that 1 Tesla is a Weber per square meter. So if we just replace that with the base units of a Weber per square meter, and we need to make sure we retain our seconds in the denominator there, because that's a Weber per square meter per second. And then we do the multiplication and we see we're left with a Weber per second, because the square meters will cancel out. So you do the math and you're going to get negative 0.004 Webers per second. And a Weber per second is also a volt. So we can just replace those units. One of the definitions of a Weber is a volt times the second. So that's a simple example of Faraday's law of induction and how it generates a voltage in a coil of wire.